Today we're going to look at the topic of semantic parsing, and this is my favorite topic of the class, and it's one of my favorite topics in NLP altogether. When I was at Google, my team was responsible for doing semantic query parsing for Google Search and for the Google Assistant. So we applied the semantic parsing techniques that we're going to look at today to billions of queries every day and in 40 major languages. Now I'm at Apple, and we use very similar techniques for query understanding for Siri. So semantic parsing is highly strategic for Google and Apple and Amazon and Microsoft. And it's also been a very hot topic in academic research over the last 5 or 10 years. Now, semantic parsing is a big topic. It's a complex topic. I think more than any of the other topics that we've covered, it draws on concepts from linguistics and logic. So I can't possibly do the topic justice in just the next hour that we have. But fortunately, if this topic catches your interest, we have an abundance of material on the website that can help you go deeper. We have a series of 4 code books that introduce a simple semantic parsing system called Sippycup. Chris has made a few screencasts that explain the main ideas in very simple and approachable terms. And there's also this terrific paper that Chris co-authored with Percy Liang in 2015 that I think conveys the main ideas of semantic parsing very clearly and very concisely. For today's lecture, I think the best that I can do is first to give you some high-level motivation for why this is a problem that you might care about, why this is an interesting and impactful problem. And second, to describe the standard approach to semantic parsing in very high-level terms. So let me begin by talking a little bit about the motivation for semantic parsing. At this point in the course, you might be asking yourself, wait, I thought we were supposed to be doing natural language understanding, but I still don't know how to build C3PO. I still don't know how to build a robot that can really understand me. The stuff that we've looked at so far, vector space models of meaning, sentiment analysis, relation extraction, they seem to capture aspects of meaning or fragments of meaning. But there's still a lot that's missing. We still don't know how to generate complete, precise representations of the meanings of full sentences. And there's still many aspects of meaning that we don't know how to capture. So for example, things like higher arity relations, or events with multiple participants, or temporal aspects. Like this example, Barack and Michelle Obama got married in 1992 in Chicago. Or logical relationships, as in no one may enter the building except policemen or firefighters. As an example, try to imagine building a natural language understanding system that could answer logic puzzles like this one. This was actually the very first project that I worked on when I was a young, eager PhD student, before I became disillusioned. This is a type of logic puzzle that appears on the LSAT exam, and it used to appear on the GRE exam as well. This is a typical example, and this is basically a constraint satisfaction problem, a CSP. So you have 6 sculptures, which you need to assign to 3 rooms while respecting some constraints that are given there. The interesting thing about this type of puzzle is it's difficult for humans and it's difficult for computers. But what makes it difficult is completely different for humans and for computers. For humans, understanding the language is easy. And in fact, the authors, I guess ETS, has taken great pains to ensure that the language is clear and unambiguous. They really want to avoid any misunderstandings where like the human reader just didn't get it. So they work hard to make the language very clear and unambiguous. For humans, the language is easy, but solving CSPs, doing the logic part of it, is hard. And that's what this is supposed to be testing. For computers, it's the other way around. For computers, solving CSPs is easy. In fact, it's trivial. For computers, understanding the language is hard. If we could build a model that would automatically translate this text into formulas of formal logic, then a theorem prover can do the rest. It'll be completely trivial for a theorem prover. But that translating this into formal logic, is far more difficult than it might at first appear. And to illustrate this, I want to take a close look at just a few specific challenges that might arise. So our challenge is build a system that can translate these words into formulas of first-order logic. One challenge is that many words have semantic idiosyncrasies. So an example is the word same. So consider this sentence: sculptures D and G must be exhibited in the same room. If you translate this into formal logic, you're probably going to get something like this. So I've glossed over some details here, like I didn't worry about existentially quantifying variables x and y, but I think it's enough to convey the basic idea. What this says is if D is in X, so D is a sculpture and X is a room, if D is in room X and G is in room Y, then X and Y must be equal to each other. Okay, so that seems straightforward, but the point I want to make is that this adjective, same, is a funny kind of adjective. And to make that clear, let me compare it to some other adjectives. Let's instead look at this sentence. Sculptures D and G must be exhibited in the red room. Think about what the logical form for that would look like. It might look something like this. If it starts off the same way, if D is in X and G is in Y, then X is red and Y is red. By the way, I'm using sort of a Lisp-like syntax here rather than standard first-order logic syntax, but hopefully it's still it doesn't really matter what the syntax is, and hopefully it's still understandable. You might quibble with my logical form here because, well, I didn't properly account for the semantics of the definite determiner, which is a very rich topic in itself, but I think that's an issue that we can safely put to the side. It's not really the main point here. The real point is, when I say the red room, or a red room, maybe would be better, I'm just asserting something about the rooms that D and G are in. I'm saying whatever room D is in, it's got to be a red room, and whatever room G is in, it's got to be a red room as well. And if I look at other adjectives, like if I change it to large room or smelly room, it's going to have the same kind of semantics. It's going to be the same mapping into a logical form. Does everybody buy that? Do these logical forms look more or less right, putting aside issues like the definite determiner? Red and large and smelly are ordinary adjectives. They're what's called intersective adjectives. They have semantics which are intersective. Same is a funny kind of adjective. It's called an anaphoric adjective. And that refers to the idea that the semantics of same refer back to something earlier in the sentence. The same room is not a specific room or even a room with a specific quality. It's just whatever room D and G are in. If you let's say you've successfully built machinery that can do semantic interpretation of this sentence and this sentence and this sentence. It can successfully handle ordinary adjectives. That same machinery is going to break down when it gets to an adjective like same, which syntactically looks identical, but semantically behaves very differently. And there are other examples too. If you're an eager young PhD student, you might think, oh, okay, I ran into a problem. No worries, I'll just fix it. I'll just make my model know about same. But then you realize there are more problems like that. There's other anaphoric adjectives like different, which have similar properties. And you might say, okay, well, I just add another epicycle to my model and I can handle that one as well. But then you start to encounter more and more and more quirky semantic phenomena that are not anaphoric adjectives, but have other kinds of idiosyncrasies that you haven't accounted for in advance. Let me give you a different kind of challenge, the challenge of scope ambiguity. And to introduce this, I'm going to use a joke from Groucho Marx. It's not a very good joke, but it is a good example of scope ambiguity. It starts off, in this country, a woman gives birth every 15 minutes. Okay, didn't know that, but all right. And then he continues, our job is to find that woman and stop her. So this joke hinges on a semantic ambiguity. When you read the first part, you're like, okay, every 15 minutes, there is some woman who gives birth. But when you get to the second part, he's giving that first sentence a different reading. Instead, there is a specific woman who gives birth every 15 minutes. That's the semantic ambiguity. It's a question of whether the universal quantifier every or the existential quantifier takes wider scope. Because I'm a language nerd, I collect examples of scope ambiguities. That's a perfectly normal thing to do, right? And I have another nice one, which has exactly the same structure. Children, there is a time and place for everything. You can see, again, it has the existential quantifier and the universal quantifier. So the standard reading is, for everything, there exists some time and place for that thing. But the alternate reading is, there is one specific time and place, which is the time for everything, right? And the joke continues. And it is called college. This is from South Park. I thought that might resonate with you guys because you're at a university. So this is the idea of scope ambiguity. How does it relate to the LSAT puzzle that I just showed you? Well, one part of that LSAT puzzle was this: no more than 3 sculptures may be exhibited in any room. So this is interesting because there's not just one possible reading here, or even 2 possible readings. There's at least 3 possible readings here, which if you rendered them as first-order logic, are quite different in terms of their logical form and their logical consequences, but all are plausible readings of this sentence. And from a computer's perspective, there's no way to know in advance which one is the correct reading. I think the most obvious one, the one that the authors intended you to get, was this one. There cannot be a room that contains more than 3 sculptures. But there's some other possible readings here. Can anybody think of another way of reading this sentence? No more than 3 sculptures may be exhibited in any room that would have a different logical form, that has different logical consequences? Yeah.
These sculptures across, like across a space of time. Like you can't have one and then take it out and then bring another one, take it out and then bring another one. So in the end, it has 3.
Oh, that's interesting.
Assume that says.
That's not one of the ones I was thinking of, but you're touching on something about whether we're talking about a single point in time or over time. Whether the assignment of sculptures to rooms could change over time. Yeah?
Is it that there cannot be no more than 3 sculptures, as long as they present in a room?
As long as they what?
They're in a room. So a sculpture is in a room?
Yeah, you could read this as no more than 3 sculptures may be exhibited in any room. Like, it doesn't matter what room it is. No more than 3 sculptures may be exhibited at all in any room. That reading of this sentence is maybe a little bit less obvious and a little bit less accessible than the first one. But I think there are ways of contextualizing this that make that reading plausible.
Are there any differences between the first and the second in this case?
Yeah.
Yes, there are. Because in the first one, a possible world, a possible configuration that's consistent with the first sentence is you have 2 sculptures in this room and 2 sculptures in that room. But that is not consistent with the second reading, which says no more than 3 may be exhibited at all.
Total, like ever.
Yeah, exactly. So they have different logical consequences depending which one you read. There's actually a third reading, which I think is even harder to get to, but I claim is still a plausible reading of the first sentence. And that one is, at most 3 sculptures have the property that they may be exhibited in any room. For other sculptures, there are restrictions on allowable rooms. So go back to that first sentence now. No more than 3 sculptures may be exhibited in any room. The other ones have restrictions, right? That's a plausible reading. It's not the most obvious reading, but it's a plausible reading. And from the perspective of a computer algorithm, like, computers don't have intuitions about which one of these things is more plausible or less plausible. So when you're building a system to map these sentences into logical forms, your model probably needs to account for all of those possibilities, because in different contexts, any one of them might be the correct interpretation. Of course, you also hope that your model will be able to make good predictions about which one is more likely and less likely. And a little bit later, we'll look at ways of building a scoring model which will help you choose among multiple possible parses, multiple interpretations of a given input. I'm not going to say anything more about the LSAT puzzle, but I could go on. There are lots more challenges. I'll just mention one other off the top of my head. There's nothing in the problem itself. Let me go back to that problem. There's nothing in the problem that says a sculpture can only be in one place at one time. There's nothing that says a sculpture can't be in two rooms at the same time. But if you just map this into first order logic and then give it to a theorem prover, the theorem prover will happily put one sculpture in two different rooms, because that's common sense knowledge, that a sculpture can't be in two different places at the same time. A human just fills that in automatically without even thinking about it. But a computer doesn't know to do that. So you have to, if you want to make this work, you have to also supply all kinds of background knowledge, which is kind of unstated in this problem. So we started this problem, as I mentioned at the beginning of my PhD, and we worked on it for about like 3 months. And the further we got into it, the more we realized we're not going to solve this problem. And that was like 15 years ago. And as far as I know, this problem remains unsolved today. This is a really hard challenge. But it looks, at first glance, like it should be achievable. OK, here's a very different kind of example. This is taken from a consulting project. Yeah.
Like graduate student kind of perspective on it. Has anyone tried to do this with a more limited scope and using something like a knowledge base for grounding? Kind of similar to what we talked about in Monday's lecture?
I'm not sure.
Yeah, I don't know either. It's a good intuition, though, that you could, a lot of the constraints that Bill was talking about might come from the domain that you're in. And that could be an interesting thing scientifically. I don't know if we're trying to do it.
Thank you.
So here's a very different kind of example. This is taken from a consulting project that I worked on when I was in grad school. And I was working with a startup that wanted to build a natural language interface to a travel reservation system. So they wanted to be able to understand and respond to natural language descriptions of travel needs like this. The idea is you'd be able to send an email to this service, and they would automatically figure out some travel plans for you. So what are some of the challenges to semantic interpretation that you see here? There's lots of them. Yeah, what's an example of ambiguity here?
Like you could do Oakland or SFO. You could do Sunday evening or Monday morning. It's like you would have to extract all of those and realize that they're the same sort of fill in the blank that they're related to.
Yeah, one kind of ambiguity here, I mean, it refers to Oakland, but it doesn't actually make it clear whether Oakland is an alternative to SFO or an alternative to Boston. Now, as a human, you know that it's an alternative to SFO. It wouldn't make sense to book a flight from SFO to Oakland. Might be fun. But an automated system, of course, that relies on world knowledge, which might not be available to an automated system. What else could make this hard? Yeah?
I guess it has to realize that the he later on refers back to the husband, and that the different flight has to be both, return flight has to be both.
That's right. You have to resolve some anaphora here and figure out what that pronoun refers back to. And there's other kinds of reference resolution here. Like, for example, Sunday evening or Monday morning. We need to figure out that that refers to the Sunday that, presumably that refers to the Sunday that follows that Friday, not the Sunday that precedes that Friday, right? So I guess we're talking about Sunday the 14th or Monday the 15th. There's something else weird here, which is that if Friday is the 12th, then Wednesday can't be the 18th. Like mathematically, that doesn't work. The Friday and Wednesday are 5 days apart, but the 12th and the 18th are 6 days apart. The human made a mistake, and the system has to deal with it somehow. Like a reasonable thing would be for the system to say, did you mean Wednesday the 17th? But unless you engineer that into the system, it's not going to be able to do it. What other challenges do you see here? Yeah.
Seems like there's also some extraneous information, like it's important that they don't want to fly on United, but the model probably doesn't need to care about why.
That's right.
Or why the husband is staying later, that sort of stuff.
Yep. So how to focus on what matters and what doesn't matter. Hating their guts is an idiom. So this gives you a flavor of some of the kinds of things that you run into when you try to do complete and precise semantic interpretation on real-world problems. This goal of complete and precise natural language understanding goes way back to the beginning. Last time, Chris mentioned the Sherdlu system, which was developed almost 50 years ago by Terry Winograd when he was a grad student at PhD. He's now a professor here, and he doesn't work on natural language understanding anymore. But this was arguably the birthplace of natural language understanding. So Sherdlu is a blocks. It's an NLU system that's grounded in a blocks world. It parses the user's input, maps it to a logical form, and then tries to interpret that logical form in its world and answer a question or take an appropriate action. I give a link to a YouTube video here, and it's worth checking out later. These slides, by the way, are linked from the website, and from there you can find your way to this YouTube video, and it's kind of a fun video to watch. And so you can say even quite complicated things like, find a block which is taller than the one you are holding and put it into the box. And it understands, and it just does the right thing. And at the time, people were totally wowed by this. I mean, I think even half a century later, this kind of elicits a wow. But certainly at that time, it really had people thinking that human-level NLU was just around the corner. But then that excessive optimism crumbled when later systems tried to deal with more realistic situations and with real-world ambiguity and complexity. Part of the reason this was achievable was that it was this very constrained blocks world that we were operating within. Another milestone for semantic parsing was the Chat80 system. This was developed around 1980 by Fernando Pereira, who's now a research director at Google. So this was basically a natural language interface to a database of geographical facts. So it could answer geographic queries like, what's the capital of France, or how many countries are in Europe, or things like that. It was implemented in Prolog, and it used a hand-built grammar and a hand-built lexicon. So there was no machine learning in sight. It was just lots and lots of rules that drove this semantic interpretation. Now here's something astonishing. It is still possible to run Chat80. Even though this code is older than most of you, you can still run it on the Stanford Rice machines. And if you want to try it yourself, here's a recipe for getting started. And it's actually really fun to kick the tires and try it out and see what works and what doesn't work. In previous years, I've actually taken time in class to do this live in class, which is kind of fun. But it's a little bit cumbersome, and I feel like maybe the educational value of it isn't worth the cost. So I'm not going to do that this time. But I want to show you some examples of some queries that it can handle. So you can ask it, like, is there more than one country in each continent? By the way, what's the right? Let's see how good you guys are at geography. No, why not? Antarctica and Australia, yeah. Funny thing is, this system doesn't think that Australia is a continent. It thinks that Australasia is a continent. So the reason it says no, it does say no, but the reason it says no is because of Antarctica, not because of Australia. What countries border Denmark? It's a pretty easy question.
Germany?
Yeah, except remember, it's 1980.
Oh, Soviet Union.
No.
East Germany?
West Germany. West Germany, yeah. It's yeah, kind of funny to step into the time machine back to the Cold War and all that. I'll skip the next two, but this one is really impressive. Which country bordering the Mediterranean borders a country that is bordered by a country whose population exceeds the population of India? Chat80 knows how to get this question right, even though it's incredibly syntactically complex. Can anybody get this one? All right, I'll let you guys think about that one.
Is the country whose population exceeds the population of India, is that Russia or China?
China.
Is it
So China's the only one.
Is the only one?
In 1980, yeah.
I'll let you think about it. No, I'll let you go try Chat80 on the rice machines. You can ask Chat80, and Chat80 will tell you the answer. By the way, one of the things that when I show this live, one of the things that I get out of it is trying out small variations. So if instead of saying what countries border Denmark, if I said what countries touch Denmark or what countries adjoin Denmark, it frequently just says, I don't understand. You change one word and it just says, I don't understand, because that other word or that other formulation, that other way of asking the question just wasn't in the hand-built grammar. The last example kind of falls in the same bucket. How far is London from Paris? It feels like a question that has very similar flavor to all the other questions. It's just another geographical question. But it turns out that no matter how you ask this question, Chat80 just says, I don't understand. It doesn't know about distances between, it knows about like areas. It'll tell you how many square miles, the total area of countries south of the equator and not in Australasia, but it can't tell you about distances between places. So it has two pretty profound limitations. One is that it only knows about certain things. It's certainly restricted to geography. Even within geography, it only knows about certain kinds of geographic facts. That's one restriction. The other restriction is on the phrasing, the allowable phrasing of questions. Even questions that it knows the answer to, you have to express your question in a certain specific way. Maybe there are a few different ways that it can handle, but there are lots of other ways that to a human are perfectly reasonable ways to ask that the system just can't handle. So on the one hand, systems like Sherdlu and Chat80 are pretty astonishing because long before most of you guys were even born, these systems demonstrated precise and complete understanding of even quite complex sentences. And by the way, they did it while running on hardware that's less powerful than my rice cooker. Admittedly, I have a really fancy rice cooker, but still, it's kind of impressive what they were able to do. But their coverage was extremely narrow. It was limited to one specific domain. And even within that domain, they were very brittle. If you ask a question this way, you get an answer. If you use just slightly different words, nothing. Today, by contrast, we have systems that exhibit vastly greater robustness and with very broad coverage, but with very fuzzy and partial understanding. So you can ask Google about just about anything, and it never says, I don't understand. But it might not exactly answer your question. If you asked Google this question about which country bordering the Mediterranean borders a country that is bordered by a country whose population exceeds the population of India, Google's not going to tell you the answer. Or actually, what it probably will do is it'll link you to my slides from last year, which maybe have the answer. But it doesn't have that complete, precise understanding that's needed to actually answer the question. Where we want to be is up here with C3PO and the pot of gold. We want to build systems that can understand precisely and completely and robustly over broad domains. Now, you might not feel super inspired by examples like that one, what's the population of the largest country, that one. Because let's be honest, who cares? But the ability to answer these highly structured, kind of database-y type of queries has lots of applications that are more compelling. So for example, if you're a policy analyst working on global warming, you want to be able to answer questions like these. And it's easy to imagine that you have a database that contains all kinds of statistics about carbon emissions. But unless you're a programmer, you probably don't know how to write SQL queries to pull out the information that you need. So it would be great to have a system where you could just type in questions like this and get the answer. Here's another example. If you grew up in America, there's a good chance that you have an Uncle Barney who is a total freak about baseball trivia. Uncle Barney would love to be able to ask questions like these, but again, he doesn't know how to write database queries. But if you can invent a semantic parsing system, maybe you can make a website and sell subscriptions, and Uncle Barney will pay you $10 a month. And here's an application that has become very important at Google and at Apple and Amazon, voice commands for getting things done. One thing to notice here is that these queries are not well served by conventional keyword-based search. Just imagine if you ask Google, how do I get to the ferry building by bike? And Google responded by showing web pages containing those terms. That would be a disappointment, because you don't want web pages containing those terms. You want a map with a blue line on it. And the only way we can draw that map is if we know where you are and we compute a route from where you are to the ferry building. And doing that requires understanding your intent in a complete and precise way. So satisfying queries like these requires mapping them into structured, machine-readable representations of meaning that we can pass to a downstream component to take action on. It requires semantic parsing. So the goal of semantic parsing is to do precise, complete interpretation of linguistic inputs and to map those inputs into structured, machine-readable representations of meaning. So a really important question is, what kind of semantic representation are we aiming at? What's our target output? And there are a lot of different possibilities, kind of depending on what the problem is and what the domain is. If the goal is to facilitate data exploration and analysis, then the right semantic representation might be a database query language like SQL. For a robot control application, you might want a custom-designed procedural language. For interpreting voice commands, you can often get away with a relatively simple meaning representation, which is based around a fixed set of high-level intents that are parameterized by specific arguments. So for example, if the query is directions to SF by train, the semantic representation might be something that first indicates that this is a travel query. So that's kind of indicating the intent here, the type of intent. And then with two parameters. One is a destination parameter, and the value there is a freebase ID, which is the freebase ID for San Francisco. And then the second parameter describes the transportation mode. And here the value is, I guess, an enum value. There's maybe like 5 different transportation modes, and transit is one of them. And so this little machine-readable expression conveys everything that you need to pass to a back-end system, which can actually like figure out the directions and draw a map and give it to the user. And similarly for other kinds of queries here. Okay, so to illustrate the central ideas of semantic parsing, we've created a simple semantic parser called Sippycup. Although it's designed for simplicity and readability, it uses methods that are commonly used at Google and Apple for semantic interpretation of user queries. And we produced a series of 4 codebooks that introduce Sippycup. So Unit 0 is kind of a high-level overview of semantic parsing. And then the remaining units demonstrate the application of Sippycup to 3 different problem domains. So Unit 1 focuses on the domain of natural language arithmetic. This is queries like 2 times 3 plus 4 as English words rather than mathematical symbols. Unit 2 focuses on the domain of travel queries. So this is queries like driving directions to Williamsburg, Virginia. which has pretty obvious applications for assistant products like Google Assistant and Alexa and Siri. And then finally, Unit 3 focuses on geographical queries, so things like how many states border the largest state. And this has a very similar flavor to the kinds of queries that Chat80 takes on. So Unit 3 kind of illustrates a modern machine learning-based approach to the same problem that the Chat80 system took on. By the way, this approach that Sippycup illustrates was pioneered first by Luc Zettelmoyer and his group at UW, and later by Percy Liang and his group here at Stanford. And so the key elements of this approach are, first, a context-free grammar, which defines the possible syntactic structures for the queries. Second, semantic attachments to the CFG rules, which enable bottom-up semantic interpretation. Third, a log linear scoring model which is learned from training data. Fourth, phrase annotators for recognizing names of people, locations, dates, times, and so on. And finally, grammar induction, inducing grammars from training data in order to quickly scale into new domains and new languages. And over the following slides, I'll talk about each of these 5 elements in turn. So let's start with the grammar. The grammar is the core of the semantic parsing system, and it has 2 parts. It has a syntactic part and a semantic part. The syntactic part is a fairly conventional context-free grammar. So we have terminals like Google and NY and me and bike and car. And then we have non-terminals, which we indicate with a $sign. So like $loc, for example, is a non-terminal. And we also use, we have a designated start symbol, which here by convention we're calling $root. So every derivation has to bottom out with $root. We're also using a notational convenience here. This question mark indicates that this element is optional. And so that's just a notational convenience. If I wanted to avoid using this, I could instead have 2 rules here. One that has $root and all this stuff without the parentheses and the question mark. And another rule which has $root and all this stuff except that. So this is just saying this could be here or it could not be here. It's optional. So this particular grammar fragment could be used to parse just a handful of queries. It could be used to parse route me to New York by car. It's one possible thing that can match this grammar. Or it could match route, I'll skip this, to, let me do a compound location, Google in New York by bike, or a handful of other queries. There's not very many queries which match this very limited fragment, but it gives you a flavor of the kinds of things that are achievable. As is typical for grammars of natural language, these grammars are usually non-deterministic. So if you've looked at CFGs in the context of programming languages, like if you took CS224U, you probably have seen deterministic grammars where there's only one possible parse, one possible interpretation for any given input. In linguistics, we typically deal with non-deterministic grammars where there are multiple possible parses for a given input. And that's important because natural language utterances are very often, I dare say usually, ambiguous. So here's an example of a parse for the input, route me to Google in New York by car. We recognize me as an optional word. We recognize Google as a $loc, a location. We recognize New York as a $loc. We then recognize loc in loc as a compound loc. We recognize bike as a $mode. And then because we've got a destination and a mode, we can use that last rule to put the whole thing together into a $root, which is the final syntactic production for a thing. So this is basically the syntactic parse, one possible syntactic parse for that input. So far, so good? So this is the syntactic part of the grammar. Okay, so given a grammar and an input query, we can generate all possible parses of the query using dynamic programming. And specifically, we use an adaptation of the well-known CYK chart parsing algorithm. So if you've ever looked at syntactic parsing before, you may have seen this. Here's how it works. The first thing we do is we rewrite the grammar so that all of the rules in the grammar are binary, or maybe unary. Binary means they only have two things on the right-hand side. What we don't want to have is 3 or 4 or 5 things on the right-hand side. We want to have at most 2 things on the right-hand side. And then what we do is we consider every span of tokens, every subspan of the whole query. And we do that bottom up. So we work our way up from very small spans, like spans of 1, up to larger and larger spans. As we go, for every span, we consider all ways of splitting that span into 2 parts. And then we consider every grammar rule whose right-hand side can match those 2 parts. And that's why it's important to make the grammar binary, so that we only have to consider splitting things in 2 and not splitting things into 3 or 4 or 5. Every time we have a grammar rule that can potentially match that right-hand side, that tells us that we have a way of making the category which is on the left-hand side of the rule. And so we can record that as a possible interpretation, a possible parse for that span. And that can be helpful as we work our way up to larger and larger spans, because it can help us build bigger things above that. We can use those categories in trying to interpret larger spans. Okay, so that's the syntax. What about the semantic part of the grammar? Every rule in the CFG can come with what's known as a semantic attachment. And I've shown the semantic attachments here in the square brackets in green. You can think of these semantic attachments as little programs that are run when the parser applies the corresponding syntax rule. And their outputs are fragments of our meaning representation. These semantic attachments basically specify how to construct the semantics for the thing on the left-hand side from the semantics for the things on the right-hand side. So for Google, this one is very straightforward. The semantics for Google is just going to be a freebase ID, which means Google. It's the entity Google. And similarly for New York. For $loc in $loc, this thing says the way to construct the semantics for this $loc is to build it up out of the semantics for this $loc and this $loc. If you've already got semantics for this $loc and this $loc, I'm going to call the first one $1 and the second one $2. And this thing says, just take the semantics for this $loc and the semantics for that $loc and stuff it into one of these S expressions with an in the front. It's a fragment of our meaning representation, and this thing tells us how to build up these pieces into larger and larger pieces. These ones are straightforward. The semantics of a dollar mode is just one of these enum values. And then the last thing that's interesting is that this one tells us how to build the semantics for the entire request. It says it's a get directions request. I guess that comes from the fact that it's a route. The destination is going to be whatever the semantics is for this non-terminal. And the mode is going to be whatever the semantics is for this non-terminal. So these semantic attachments tell me exactly how to construct my semantic representation from smaller pieces building up to larger and larger pieces. So here's our example parse again, but this time I've added in green the semantic yield associated with each node in the parse tree. By the way, if you're a linguist, this is basically Montague semantics. It's bottom-up, syntax-driven semantic construction. So first we construct the semantics for Google and for New York as freebase IDs, and for bike as an enum value. Then we combine these two to get the semantics for the compound location up there. And finally, we combine everything to get the semantics for the get directions request at the top. Okay, let me pause there because that was a lot to absorb. Any questions so far? Okay, let me keep going. So the next question is, how do we recognize names and dates and numbers and things like that? We could do it all in the grammar. And that's just what I did with Google and New York here. I have directly in my grammar something that associates the string Google with the semantics, which is a freebase ID. And I could do that for long, long lists of entities. And I could also do it for dates and numbers and things like that. But if I do that, it's going to mean adding lots and lots, like millions of rules to my grammar, which is going to be really messy and cumbersome and brittle and difficult to maintain. And it's going to have limited coverage anyways. I mean, I can't possibly put every possible date or every possible number into my grammar. So instead, what we're going to do is leverage special purpose annotators for phrases that describe entities, locations, names, numbers, dates, times, and things like that. So here's an example. The example query is reserve Gary Danko with Tom next Friday. And so here I'm imagining that we have 3 different annotators that are going to help us interpret this query. And they basically function like black boxes which run first before the syntactic machinery gets to work and can hand their results to the syntactic machinery. So first I imagine that I have a freebase annotator. And this thing, its job is to look for entity mentions that are things that freebase knows about. And it recognizes this phrase, this string, Gary Danko, and it says, oh, I know about that. That's freebase entity, this thing. And it tells me this is a dollar restaurant, which I think it figured out from, it is also able to generate lots of metadata because it has all of freebase at its disposal, right? It knows about freebase. And so it's able to look this thing up and figure out it's a restaurant, and it knows to generate that syntactic category. And then it also generates this helpful metadata that can be passed downstream. So for example, it has a confidence score that says how sure it is that it's made the right interpretation here. And that confidence score can be passed through and be an input to scoring the interpretation later on. I also imagine that we have a contact annotator which recognizes this string, Tom, and it says, oh, Tom, I know who that is. It's this user ID, and he has this email. So obviously, the only way that can work is if the contact annotator knows who issued the request. It knows that this request is from a specific user, and that user has a friend named Tom, and this is his user ID. So it needs access to some personal information in order to ground the semantics with a specific user ID. And finally, a date annotator, it recognizes this phrase next Friday, and it says, oh, I know how to generate semantics for that. Next Friday means May 10th, 2019. And it was able to do that because it knows when the query was issued and therefore is able to interpret next Friday appropriately. So next Friday is an indexical expression, but to ground it correctly, I need to know something about when the query came from. So we have these annotators that can run essentially as black box modules, run over the input query, generate hypotheses about how to interpret small spans, and record those hypotheses as inputs to the syntactic machinery that will get rolling afterwards. Okay, a pervasive problem, yes?
So just going back to that approach.
Yeah.
What exactly is the issue it's tackling? Like when you first pitched sort of the problem, I thought a solution could be to affect the annotation itself. So rather than saying location goes to New York, you could say location goes to span, and then the invocation would be invoke lookup on the span. Rather than running the entity recognition first, you could run the semantic parser, and it would identify the span and then pass it to the annotator. Is there a reason why we prefer to run the annotator first?
I think maybe what you're suggesting is that the parsing could happen top-down instead of bottom-up. Does that sound right?
That could be, yeah.
And that's, conceptually, that's definitely possible. And like when you, for example, if you've taken CS143, you study lots of different approaches to parsing, and some of them are bottom-up, and some of them are top-down, and some of them are a mix of both. And all of them are conceptually possible, but there can be big differences as far as the efficiency of parsing. And particularly for natural language, which is so highly ambiguous, top-down parsing turns out to be prohibitively expensive. And bottom-up parsing is way more efficient because you can eliminate unlikely possibilities early in the process. When I was working on this problem at Google, the grammars that we were working with, it was commonplace for even very pedestrian inputs to have literally thousands of possible parses. In fact, that's the next point I'm going to turn to, is ambiguity. And when there are thousands of possible parses, you need to do pruning fairly early in the process. We would use what's called a beam search to basically maintain, as the process of parsing is happening, to maintain a finite length list of the most promising possibilities and aggressively prune beyond that list. And that was the only way to keep the search for a plausible parse manageable.
So just following up on that, when we do the annotations, it does help us to limit the number of possible parses. And so that's one of the big advantages to running annotator first.
Yeah. Yeah.
Thank you.
Yep. So this problem of ambiguity is, this is a problem that's pervasive throughout language, and certainly big challenge for semantic parsing. And ambiguity can include both syntactic ambiguity and semantic ambiguity. So here's an example. The input is mission bicycle directions. So imagine the user issues this query to Siri or to the Google Assistant. One possible interpretation for that is that we want to get to the mission by bike. I want mission bicycle direct. I want to ride my bike to the mission. That's certainly a possible interpretation. It turns out that there's a bike shop called Mission Bicycle. So another possible interpretation is I want directions to Mission Bicycle, and I'm not specifying a transportation mode. I just want direct. Maybe I want driving directions, but where I want to go is Mission Bicycle. So here I show these two different parses for this query. In this one, mission is a location, bicycle is a mode. In this one, mission bicycle is the location, and I'm not specifying a mode. In this case, in this example, there's only two possible parses. But as I mentioned a moment ago, in complex domains, with rich grammars, it's commonplace that there are tens or hundreds or even thousands of possible parses. So if our grammar supports multiple interpretations, how do we know which one to choose? The answer is with a scoring function. We need a way to score the different candidates so that we can figure out which one is the most plausible. And one approach to doing that is with a log linear model to score alternative derivations. So a little bit of terminology here. I'm going to call the input, that is the query, the natural language query, X. I'm going to call the derivation, or parse, so that's the syntactic parse tree with all of its semantic attachments. I'm going to call that Z. And I'm going to use Y to designate the semantic yield. So that means the final semantics. It's basically the semantics that you get at the root node in the parse tree. By the way, Z completely determines Y. But for any given X, you may have lots of candidate Zs and correspondingly lots of candidate Ys. So to build this scoring function, what we're going to do is first define a feature representation which captures the key characteristics of the input X, the candidate parse, Z, and the candidate semantics, Y. There's a lot of room for variation in the feature representation, but just to give you a flavor of like some commonly used features, your feature representation might include an indicator function, which is 1 just in case the input contains the word to, and the candidate semantics contains a destination parameter. Presumably, like intuitively makes sense, those two things are likely to go together. And so seeing those together might count as weak evidence. It's hardly proof, but it might count as weak evidence that this is actually a good parse. Or you might have features which capture, again, indicator features, so Boolean features, which capture the occurrence of specific CFG rules or specific categories, the dollar things, in the candidate parse. The intuition here is some rules in your grammar might be much more likely or unlikely than others to participate in good parses, in valid parses. You might not be able to anticipate that in advance, but if you have features like these, then you have the opportunity to learn that from data. You can learn from your data that some rules work much better than others. Another kind of feature you might include is features which pass through the confidence score that you got from an annotator. Presumably, if the annotator is really confident, that makes it more plausible that a parse that includes that annotation is a good parse. There's lots of room for variation in the feature representation, but once you have a feature representation, the score for a derivation, the score for a parse, z, will just be the dot product of the feature vector and a weight vector theta, which is learned from training data. And once you have a score, you can turn the score into a probability in the usual way by using the softmax function. So the next question is, where do we get this thing from? Where do we get the weight vector theta? This is basically the parameters of our scoring model. Well, we're going to get it from data. We're going to estimate those model parameters from training data, and we can do it using a variant of the EM algorithm. The reason for using the EM algorithm is that our training data consists of pairs of inputs x and target semantics y, but the training data doesn't include the correct parse trees z. So there could be multiple parse trees that yield the same semantics. So we have to treat those z's as latent variables, and that's what the EM algorithm is good at. Yeah?
Could you elaborate a little more on what the EM algorithm is? I'm not familiar with it.
Yeah, I'll try to explain it in application to this specific application. The EM algorithm alternates between E step and an M step. EM stands for expectation maximization. And in the E step, what we do here is use the current model parameters theta to parse the inputs in our training data, and for each input x, generate an n-best list of possible parses. So we're just parsing all the inputs using our current model. Then in the M step, we're going to change the weights of the model. And specifically, we change the weights to put more probability mass on the elements of the n-best list that actually generated the correct semantics. In the n-best list, some of them are going to have good semantics which match the target. Some of them will not. And we want to shift the probability mass towards the ones that match the target semantics. And then we go back to the E step and do it again. We reparse everything using our updated weights that could cause the n-best list to shift around. And we keep doing that back and forth between the E step and the M step. So these updates to the models are basically SGD updates. This is kind of like a stochastic gradient descent algorithm. And the weights will adjust gradually over time toward weights that are more and more successful in generating the target parses for our training data. Okay, so we've got a grammar, it's got syntax rules, it's got semantic attachments, there's ambiguity, we have a scoring function, we've learned the scoring function from data. The next question is, where do the grammar rules come from? And the answer really depends on what domain you're working in. If it's a small, simple domain, then grammars with a few dozen or a few hundred rules are commonly enough. And at that scale, it's practical to write grammars manually. You just think about the domain and look at lots of example queries and just manually generate some rules that will capture, that will cover the set of input, the set of inputs properly. But that's not the common situation. The common situation is you're in a large, complex domain, and you need thousands of rules to model the domain well. And at that scale, it's just not feasible to write down all the rules manually. So instead, we want to learn the rules automatically from training data. And this is the challenge of grammar induction, and it's where some of the most interesting research work lies. One strategy for grammar induction, which it's a very simplistic strategy, but it's illustrated in Unit 1 of the Sippycup codebooks. The idea is simply to generate all possible rules and add them to your grammar, and then to use standard parameter learning to learn weights for each rule, to learn which rules are most likely to contribute to a successful parse. So what does all possible rules mean? It basically means all ways of combining the symbols of your semantic representation, your sort of semantic, your language of formal semantics, all ways of combining those symbols into syntax rules. Every possible right-hand side, every possible left-hand side, the cross product of all those things. And if we add all those rules to our grammar, then we can generate a huge variety of different parses. Most of them are bad, but we can use the weight learning that I talked about on the previous slide to learn from data which ones are good and which ones are bad. This works, but it comes at a heavy cost because generating all possible rules leads to an exponential blowup in the number of possible parses and consequently in the time that's required for parsing. And if you work your way through Sippycup Unit 1, you'll see this illustrated very vividly. So more sophisticated approaches to grammar induction look for ways to be far more selective about introducing new grammar rules and also ways to prune them aggressively when they're not contributing to successful parses, to keep the size of the grammar manageable so that training can still run in a feasible amount of time. So we've talked about two different ways of using training data in this process. One way of using training data is to induce rules of the grammar, to figure out which syntactic productions should be part of the grammar. The other way of using data is to estimate the parameters of our linear scoring model. And these two ways of using data are both really important and kind of work hand in hand. So this kind of underscores the importance of data for making this whole thing work. You can't do grammar induction, and you can't learn the parameters of your scoring model without training data. And not just a little bit of data. To really make this work, you want massive amounts of data. So organizations that are doing this at scale, like Google and Apple, invest a lot of money in data annotation, using proprietary crowdsourcing platforms similar to Mechanical Turk. So paying graders, paying human annotators to look at example input queries and write down the target semantics for those queries so that we can then train machine learning systems to capture that. However, that's really expensive. Labeling examples with target semantics is slow and laborious and costs a lot of money. So another really productive direction has been to enable learning from indirect supervision. An idea pioneered by Percy Liang is the idea of learning from denotations. So denotation basically means if your semantic representation is something that can be executed or evaluated in some way, that execution or evaluation could result in something that's a lot simpler and more intuitive for a human annotator to produce. So an example here, I should have put an example on the slide. An example might be like, what's the capital of the largest state in the United States. The semantics for that might be some kind of complex logical formula that literally says, except in logical language instead of English, what is the capital of the largest state. The denotation of that semantics would be the answer to the question, like Austin? No, Juneau, yes. I guess if we're talking about large in terms of area, right? What is the capital of the largest state? Juneau, Alaska. So that's the denotation. If your training data consists of inputs, like what is the capital of the largest state, paired with logical forms, we can learn very effectively from that, but it's hard to produce that training data because it's hard to get human annotators to produce those logical forms. And at Google and Apple, we figured out all kinds of tricks to make that a little bit easier for ordinary people to produce logical forms, but it's an intrinsically hard problem. It's much easier to get ordinary human annotators to produce the answers, like Juneau. And so if we can have training data that says, what's the capital of the largest state? Juneau. If we can figure out a way to learn from that kind of data, we'll be able to get lots more data and the benefit of learning from that data. So that's the idea of learning from denotations. This is a really powerful idea, and it's illustrated, again, in Unit 1 of Sippycup, where the domain is natural language arithmetic. So there, the donations are just the answer to a simple arithmetical computation. Okay, so to recap, the key ingredients of this approach to semantic parsing are CFGs with semantic attachments, log linear scoring models, annotators, grammar induction, and above all, lots and lots of training data. I hope that that's enough of a high-level overview that if this topic interests you, you'll be able to dive into the Sippycup codebooks, start reading some papers, and get a much more concrete sense of how all this stuff fits together and how all of this works. But I think I'll stop there for today.